Imagine a physical object that perfectly remembers every single thing it has ever done, while simultaneously suffering from total blank slate amnesia. This sounds like a philosophical riddle designed to trick your brain, but physicists have recently proven this exact behavior in the lab. We navigate our daily lives assuming the physical world is entirely concrete. A table is a table, and its physical properties exist regardless of whether anyone is in the room looking at it. When memory and amnesia coexist, it suggests that the state of an object is no longer independent of the person measuring it. To see how strange this is, we first have to look at how normal objects handle their own history. Just think about a rolling billiard ball. Where that ball goes next depends entirely on how fast it's moving and what direction it's pointing right now. The physics equation doesn't care who hit it 3 minutes ago. Its history is irrelevant. This shows the strict divide we're used to. On one side, systems governed by memory use past data to map the future. On the other, memoryless systems move forward independently, reacting only to the present. In our macro world, these are mutually exclusive. Yet the moment we shrink our focus down to the subatomic level, that rigid separation dissolves into a blur of possibilities. Welcome to the quantum realm. Down here, particles don't follow single, straight lines. They naturally exist in overlapping dual states. And scientists have discovered something remarkable about this space. A quantum system's ability to remember its past is not an inherent physical trait, but a state dictated by our presence. These systems aren't randomly swapping between amnesia and perfect recall on their own. It is the specific choice of the observer that forces the system to lock into one of those realities. Physicists call this the observer's paradox. The act of measurement forces the system to reveal one specific face to the outside world, while the other face vanishes. At this microscopic scale, physical memory is transformed from a fixed constant into a subjective reaction to being measured. We can see this paradox in action through this geometric model of the experiment. When scientists focus their measurement directly on the internal nodes of the system, a timeline of past states illuminates. Because we looked at the internal structure, the system's past states alter its future trajectory. It demonstrates perfect memory. But if scientists pivot their measurement away from the core to scan only the system's external properties, that internal timeline instantly disappears. The system loses all connection to its past history and acts with total amnesia. The physical particles in the experiment never changed. Only our perspective changed, demonstrating that the observer's choice determines which version of physical reality the system expresses. These results are now being applied to the engineering of stable quantum computers. This qubit faces constant bombardment from noise, external interference that shatters fragile quantum states, a persistent obstacle to reliable processing. By applying a measurement filter, engineers use the observer's paradox to force amnesia regarding its environment. The system ignores the destructive outside noise, as if it doesn't exist, while the internal measurement continues to track the vital computational data. This ability to toggle the memory of a system provides a potential path toward protecting quantum information from the chaotic interference of the outside world. Beyond the computers and the labs, the experiment leaves us with a deeper question about the nature of reality itself. If a trait as basic as memory materializes only when provoked by an observer, it suggests the universe isn't a collection of fixed, independent objects. Instead, the properties of these systems seem to remain fluid until we interact with them. By choosing how we observe a system, we participate in how its physical reality is manifested.